Hello everyone, welcome to another, let me open the video. Welcome to another our meetup sessions, one of our meetup sessions. Today we are going to finish our discussions on A/B test. Last week we couldn't meet, I wasn't feeling well, so sorry for postponing the meeting. So this week we are here. Hopefully we are going to finish A/B test today, and then from next week we are going to start talking about we are going to continue with our discussion on time series, right? So let's just remember where we left, because there was 1 week of gap, and then I'm not sure if we remember or if the same people are here. I'm not sure about that. So let me share my screen first. Okay. So you don't need to have any any notebook, any file or any kind of code to follow this session. We are going to do everything together. So if you just have one blank, the Jupyter Lab or Jupyter Notebook in front of you, if you don't have it, just open Google Colab, and then you can simply follow what I'm trying to do. So we are going to do some coding this time. Again, we are going to finish our discussion on A/B test. I'm just going to talk about how we can evaluate an A/B test. So once we run the A/B test, we get the results, how we can evaluate the A/B tests. Before starting evaluation of A/B tests, let's remember where we left last time. Last time, I think we were talking about power and significance, type 1 and type 2 errors. Remember that? So alpha and beta values. So these are the things we discussed last time. Actually, I tried to write a code here to simulate how we can determine, how we can actually visualize beta. So the area corresponding to beta and the area corresponding to 1 minus beta. This orange area, so let's remember, this blue line is representing our null hypothesis, and this orange colored line is representing our alternative hypothesis. And this orange area is representing beta, and this blue area is representing alpha. Okay, Z alpha actually, and then Z beta, or you can, if this is double-sided test, you can simply call it Z alpha over 2 and Z beta over 2. So these are some mathematical details, but what this figure tells us was important, right? If you remember, we said if you want to reduce beta, in other words, increase the power of your test. Remember, power is 1 minus beta. To increase power of your test, you need to increase your alpha. But then if you increase your alpha, you are increasing the chance for a type 1 error. So let's remember what type 1 and type 2 were corresponding to, type 1 and type 2 error. So first of all, we were trying to test a hypothesis. The hypothesis had a null hypothesis. It had 2 components, null and the alternative hypothesis, right? Let's call it A, actually. It's going to be better. So null and then alternative. Okay. So we are going to try to reject null hypothesis. Again, remember some details here where they're not going to say that alternative is correct. So there is no way we can prove that the alternative hypothesis is correct. We can simply say that we have enough evidence to reject the null hypothesis, or we have enough evidence not to reject, so accept the null hypothesis. So we're not talking about whether the alternative one is correct or not, because there might be so many alternatives when null is not correct, right? But picking one of the alternatives, we are trying to see if we have enough evidence to reject the null hypothesis. Okay, so what if the null hypothesis is correct? Let's say you are running a test. Again, remember the example we used last time. So you're trying to place a button on the website, and then the button currently has blue color. What if you change blue color to red? You're just trying to see if this has any impact on people clicking on this button, right? So your null hypothesis is going to be very simple in this case. You're simply going to say that nothing will change. If I change the color from blue to red, people will not going to react to this change, okay? So that is your null hypothesis. Your alternative will be people are going to react to this change. They can react in 2 ways. Either the number of people clicking on the button will reduce or increase. Let's say it will increase. That will be our alternative hypothesis. In this case, we have only two options, right? Blue and red. Now, what if the null hypothesis is correct? Means when we change the color from blue to red, it's not going to have any impact on people's behavior. Okay, what if the null is correct? And then we ran the test, and then we got the results. And the results suggested us that we should actually reject the null hypothesis. When null hypothesis is correct, in reality, changing the color of the button has no impact on people, but somehow our experiment results suggested that it has an impact. So this result is actually incorrect, right? So when null hypothesis is correct, what happens if we reject the null hypothesis? So when we reject the null hypothesis, when null hypothesis is correct, what we are doing is actually we are making a type 1 error, right? So when null is correct, we are incorrectly rejecting the null hypothesis. That is type 1 error. So this type 1 error, the probability of rejecting the null hypothesis when it is correct is actually equal to this alpha value, okay? The alpha value that we choose. So in general, in literature, we choose alpha equals 0.5. Again, this alpha value is corresponding to this blue area. If this is a two-sided test, right, two-tailed test, then this is going to be alpha over 2. Or you can simply say your alpha is 0.1, and this area will be equal to 0.05, right? So this blue area is correspond. Again, this blue line is representing your null hypothesis. This blue region is the region where you conducted an experiment result is falling into this region. That means whatever has happened, right? Whatever has happened, whatever the result you get, that result is a so rare case if you assume that that result is coming from the distribution that you think belongs to the null hypothesis. All right. So this result, the experiment result, is so rare that it is hard to accept that it is coming from the distribution, which is this blue line corresponding to your null hypothesis. That's why you are rejecting your null hypothesis. You are saying that it is so rare that I would expect a result from my null hypothesis. That's why I'm saying that I have enough statistical evidence that I can reject null hypothesis. I'm not saying alternative is correct. But then it might be the case that your null was actually correct. But even though it is rare, you get this experiment result. So yeah, it is rare, but it's still part of the distribution. That means your null hypothesis was correct, but somehow the result came from a very rare value. That means when null was correct, you incorrectly rejecting the null hypothesis, thinking that this rare event is actually suggesting the null is actually incorrect, right? So that is your type 1 error. Okay, so I'm just going a little bit fast because we already discussed this. How about type 2 error? When we talked about type 2 error, we said, how about the null hypothesis being incorrect? So if my experiment gives me some result where the result, the p-value, okay, where the result is actually the statistic of the test is actually falling to the left of this red line. Please don't see this orange line for now. Let's focus on this blue line. If my test result is giving me some statistic value which is falling to the left of this red line, that means my result is coming from this. If I assume that my result is coming from this blue distribution, right? And if it is falling to the left of this red line, somewhere from -infinity to, I don't know, to 1.8, right? So 1.96 actually. So then I'm going to make this the following. If my result is up to this red line, then it is likely that this result is actually coming from this distribution. Okay, because it makes sense to make that assumption. But again, maybe maybe the reality out there is that our test result is coming from another distribution, this orange distribution, which is the alternative one. Even though it is so rare for that result to come from this orange distribution, it happens that it is coming from a value to the left of red. You see, so this value here to the left of red can both belong to blue and orange, but it is more likely that it belongs to blue than to orange, because orange has a very small area on the left of this red line. So because I have the results coming from a region where it is more likely that it will come from this blue distribution, I'm going to assume that, oh, my result is actually more likely to be coming from the null hypothesis versus the alternative hypothesis. That means I'm going to assume that my null hypothesis is correct. But in reality, even though it is so rare for this result to come from the orange distribution, it came from the orange distribution, right? So that means my null hypothesis was actually incorrect in reality, but because of the results I received, right, I am going to accept null hypothesis. I'm just making an error here. That error is called type 2 error, right? Type 2 error. And this type 2 error is corresponding to your beta value. Again, we are going to choose our beta value to be equal to 0.2 in general. So 1 minus beta is the power of our test. Okay, so I think so far, again, if you have any questions, please let me know. I'm going to check the questions from time to time, but this was just an overview of what we discussed last time. So again, George, so there is nothing to actually share. This is just a bunch of notes. As I promised before, after this class, I'm going to put this at GitHub and then share the link with you guys. But right now, there is nothing, actually no data, no code in this file. So I'm just going to type everything. You can type with me. So in type 2 error, more likely we reject alternative type 2 error is the case where we are rejecting, we are accepting the null hypothesis, even though null hypothesis is incorrect. All right, type 2 error. Okay. Yeah, please ask your question in the QA session so that I'm not going to miss any of that. So how long the session today? I'm hoping to finish it in 40 minutes. All right. Okay, now here is the next thing that we are going to look at. What we are going to check now is, so far, we discussed what is alpha value, which is the significance level, which is the type 1 error. What is beta value, which is indicating the power. 1 minus beta is the power of our test. So these are two values that I'm going to assign. Okay, so these are two values that as the person who's going to be running this experiment, I'm going to assign these values. I'm going to say for a specific alpha and for a specific beta value, I'm going to evaluate my test results. So one more thing that I need to make a decision, I will give a value before I run the experiment is D, which is the minimum effect. So your test results might be significant in terms of statistics and say statistically significant. But is it also significant for you to consider this change in business? So let's say statistically, changing from blue to red is significant. That means there is an effect, statistically significant effect, changing the color of the button from blue to red. But business-wise, does it make sense to make this change business-wise? So that is, maybe you are going to work a little bit on this, and then you're going to assign a value to D. That will represent the minimum effect. Minimum effect in this case is, let me make a little bit of explanation here, the difference between P naught and P alternative. So P, remember, is the ratio of people who clicked on the button. So you are going to look for a meaningful difference between the ratio of people who clicked on blue button versus who clicked on red button. If that ratio increases for some number, let's say from 0.6 to 0.7, that 0.1 increase in the click may be beneficial for your business. Okay, so you're going to incur some cost to make that change, right? So, and then you're going to benefit maybe from that change. So benefit minus cost, right? So the profit, is it enough for you to make this change? So that is going to determine this D. Again, what is D? The difference between P alternative, actually it's going to be P alternative minus P naught, right? P0. If that difference is high enough, then you're going to make the change. So given these three values, which you decide before you run the experiment, now you are going to determine the size of the test in terms of how many people are going to be taking this test, right? So in this A/B test, how many people? Remember, I'm going to have two groups, right? Group 1 and group 2. So, and then I'm going to make them equal size groups. How many people I'm going to have in total? In total, I'm going to have in my experiment, so that I can confidently follow the results given these alpha, beta, and D values. Okay, that is the next question. Now, in many tutorials or books, you are going to directly see this value here. So N equals 16 times sigma squared divided by D squared. So you're going to see this value. And then this value, when you follow this formula here, you're going to get a reasonable N value, number of people taking the test value. All right. But let's take one step back, and then I'm not going to prove the formula here. It's going to take longer than that. But let's take one step back and then try to understand where this number is coming from, because if you understand that, it is going to help us answer the following questions. And these questions might be asked in an interview, right? So if somebody says, hey, if I decrease my alpha, because these are values you are going to make a decision, right, about. You're going to decide what these values should be before you run the test. Now, I'm just wondering, do you know the impact of your decision? What if you get a smaller alpha? What do you expect? For smaller alpha, do you expect N is going to go up or down? What if a smaller beta or smaller variance, sigma, which I didn't talk about, but the variance of the pooled data, or the smaller delta, which is D? So do you know the impact of your decision on how many people are going to take this test? Do you know that? So that's why maybe before we get into this 16 sigma squared D squared, just take one step back and then try to understand where this, again, I already have some material giving me how I obtain this formula. I don't want to go beyond this. Okay, it's going to be another maybe full session to talk about this. Let's not get into it. But if possible, don't memorize this. Don't memorize this. But if possible, have some idea like this. So this is a fraction. In the denominator, I have D. In the numerator, so I know which values are in the numerator. In the numerator, I have the sigma, and I have 1 minus alpha, not alpha, 1 minus alpha and 1 minus beta. So if you can take this picture in your mind, in the numerator, I have 1 minus alpha and 1 minus beta and sigma. In the denominator, I have the moment you have this picture in your mind, you're going to answer these questions easily. So if in the numerator, I have 1 minus alpha, if I decrease alpha, then I need more number of N, because 1 minus alpha, if I decrease alpha, I need more number of N. If I decrease beta, again, I need more number of N. If I decrease sigma, I'm going to get less number of N. If I decrease D, and again, because it's in the denominator, I'm going to have more number of N. So just a very simple, actually, algebra here. But the thing is, if you just take this picture to your mind, in the numerator, I have these three variables. In the denominator, I have this variable. Then you can easily, without hesitating, you can easily say what will happen to N if I increase N, alpha, and beta. Now, let's spend a couple of more minutes to understand the logic behind this. Okay, so this way, we are not just going to memorize it, but we are going to understand it. Why? So remember this alpha. I'm going up here. Alpha is representing this area. You see this area representing this. What is this area? This is the area where I'm going to make a type 1 error. All right. I'm going to make a type 1 error. So 1 minus alpha means I'm going to reduce this error. So for me to reduce the error probability, I need to have more samples. It's that simple. So if I reduce alpha, this area is going to shrink. This blue area is going to shrink. That means I'm going to reduce the probability of type 1 error to, that means I want to be more confident that I'm not going to make an error. How can you be more confident and then think that you're not going to make an error? So that means you're going to collect more data. That means you need more number of objects or subjects in your test, right? So that's, I mean, intuition behind why when alpha is decreasing, our n is going to. Again, same thing goes for beta. Remember, this orange area is representing beta, which is your type 2 error. What was type 2 error? When your null hypothesis is incorrect, you're not going to reject it. You're going to accept it. When your hypothesis is null hypothesis isn't incorrect, you are going to accept it. So this region, this orange region, is representing our type 2 error. Again, when I decrease beta, this area is decreasing. That means I'm decreasing the probability that I'm going to have a type 2 error. So what is the cost for that? What is the cost that I'm going to increase my confidence, reduce my error probability? I'm going to have more number of samples in my data set. That means I'm going to collect more data. I'm going to ask more people so that I'm going to feel more comfortable. So reducing type 1 and type 2 error requires more number of subjects in your test. Okay, that is the intuition for why when you decrease alpha, when you decrease beta, your number of n is increasing. Another thing is when we decrease the sigma, they are going to have less. We are going to need less number of people. Again, sigma is representing how it's representing how the distribution is spreading around the mean, right? So again, just think about it. If my sigma is small, then this curve, this bell shape, is going to be squeezed inside. When it is squeezed inside, less area, blue area, and less orange area is going to be left to the left and to the right of this red line. In other words, I'm reducing my type 1 and type 2 error rate again, right? So that means if I reduce my sigma, then I am reducing my error probability, then I don't need that many people. So I'm reducing the number of people I need for this experiment. So reducing sigma, the variance, in this case, standard deviation, sigma squared is the variance, reducing sigma is going to shrink this bell curve inside. So that's what sigma is representing, how wide the curve is, right? When you reduce the sigma, the curve is going to shrink. When the curve shrinks, these two areas are going to shrink too, right? That's why I don't need that many people. For D, that's very intuitive. D is representing the distance between P0 and P alternative. It's almost like the distance between the center of this guy and center of this guy. The more distance, the more the smaller the distance is, again, I need more and more people to reduce my error rate. I need more and more people to reduce my error rate when the distance between true and the null hypothesis is reduced. So that I need to have more people so that I can ensure that this small distance is representing some significant change. Okay, again, that's my intuitive explanation on why this equation is holding. If you have another explanation, a better sounding explanation, easier one, please share with us. So you don't need to memorize this whole what is that formula. Again, the picture in your mind is there is a fraction. The numerator has sigma, 1 minus alpha, 1 minus beta. The denominator has d. So given this picture, I can answer these questions. Also, I have some intuition about the impact of alpha, beta, and d on number of people taking the test, so that I can also give some answers for that. So let me check if we have any questions. When I decrease beta, my alpha will decrease. And how should I think the size of the, if you decrease beta, if you want to decrease beta, you need to decrease alpha. If you decrease beta, your alpha is not going to decrease, right? So if you want to decrease beta, you need to decrease alpha, right? But so to decrease beta, when you decrease beta, your alpha may not change. When you decrease beta, your alpha may not change, right? So one way to do is, if you want to decrease beta, you need to decrease alpha. I don't know the other way is gonna work, right? So I need to think a little bit about that, Engin. So how should I think the size of the experiment? Again, when you decrease alpha, your beta is going to decrease. And because both are decreasing, this time you're going to have this double effect on your number of experiments, right? So I see the question. I see why you're asking this question. When you decrease alpha, your beta is going to decrease because the area to the left of the red line is going to decrease. I see. Oh. So let me think about this question, Engin. All right. So, but simply, let me tell you this. I'm going to set alpha and beta values. If I want to have in this case a smaller beta, I might think about decreasing my alpha. But in the industry, in general, there are two values that we use. That's why we come up with this value 16 sigma squared here. So in general, we set beta to 0.2 and alpha to 0.05. So given these two values, and then assuming that sigma squared is same for the both groups, 2 times sigma squared is coming from these two sigmas, and then 1.96 is the z value of 1 minus alpha over 2, and 0.84 is the z value of beta, 1 minus beta. And then we come up with this value, 16 sigma squared d squared. Again, sigma squared because we assume the same standard deviation for null and alternative distributions. And then 1.96, 0.84, 16 is coming from our assumptions for beta and alpha. Yes, I understand that these two values are, there is a trade-off between these two values. When we decrease one of them, the other one is going to increase. Given our assumptions about, let's say, okay, let's do this way. I think the answer to your question might be the following. Again, I need to think a little bit more about that. If I fix n, okay, if I fix n number of test takers, then when I decrease alpha, my beta is going to increase. So then there is this trade-off between alpha and beta. But without fixing n, I can assume any value for alpha and beta, and then I can find the corresponding n. I think that will be the answer to your question. But if I fix n, then I can observe the trade-off between alpha and beta values when I fix n. I think that will be the answer to your question, because there is no other way. So when I fix n, if I increase this value is going to decrease, right? So there is a trade-off. But without fixing n, you can assume any value for these guys. Okay, so let me continue. That was a good question. Thank you. Could you go over the explanation for D again, please? So D is representing the distance between the ratio of people who clicked on the blue button, which is the current case, versus the ratio of people who clicked on the red button. So remember, that's why we ran this test. Currently, I have blue color on the buttons, but I want to change this to red. So I have two groups of people. The first group are taking the blue button website. The second group is taking the red button website. So P0 is representing ratio of people who clicked on the blue button in that group. Red is representing the ratio of people who clicked on the red button. All right. So I want to see a certain distance between PA and P0, PA minus P0. So P is small. Right? That means I'm going to make a business decision here. I'm just trying to see if I should change the color from blue to red. When am I going to make that change? If I see that it is worth making that change, that means if I change from blue to red, if I see an increase, let's say right now, the ratio of people who clicked on the button is 0.6. And then when I change the color, I see that the ratio increases to 0.8. So the difference is 0.2. So is this difference making any sense in terms of business? So if I make that change, there is some cost I'm going to incur, and there is some benefit I'm going to receive. So benefit minus cost. So making this change 0.2 or marginal increase, 0.2 increase in ratio of people who clicked on red versus blue, is it business-wide reasonable for me? So I'm going to make that decision about this. So I'm going to say minimum effect will be, say, 0.1. After 0.1, I'm going to be on the profit side. That means if I see a jump from 0.6 to 0.7, I'll be fine. As long as it is at least 0.1 difference between alternate and null hypothesis. So that is D value, which you need to make a decision about. Right? Okay. So there is no material from the previous lecture. I think the recordings are available, Ibrahim, so you can check the recordings at the YouTube channel. Okay, so again, there is no notebook. I'm just typing I will just type the code in a minute. Okay, there is no what is that data or any code that you need to have to follow this class today. All right, I hope I was able to answer the questions, and if not, please let me know if you have any answers or any suggestions you would like to make. Please don't hesitate. So this is, now we are almost ready to begin evaluating our A/B test. Okay, so I think we have a good foundation on what is going on. We started from the very beginning. If you check the first lecture, right, we started from the very beginning where this ratio is coming from, right? So why we are going to use Z-test, and then why this hypothesis testing suddenly appearing. So I think step by step we learned about all these details. Now let us assume some numbers for an experiment and see how we can evaluate this experiment. Okay. One thing before I just remembered one thing before we start evaluation. Let's say you get N number of people who are going to take this test. All right. So the next thing you are going to decide is duration. Okay, how long this test is going to take. So once you get N, okay, for a reasonable alpha, beta, and D values, right? Once you get N, so the duration is actually it's going to be simple based on your experience with your business, right? So I mean, how many people you are expecting to collect daily basis, right? So let's say your N is 10,000. How many people you are expecting to have, or you are going to? So there are two things here you can consider. One is how many people you are expecting to receive on your website. If that number, the number coming to your site is not that large, then you're going to divide this N by number of visitors, right? So that is going to determine the natural length of the experiment. Now, if this duration is too long, then by time you're going to lose the impact of the experiments, people are going to get accustomed to the change, so you're not going to see the impact clearly. So you should not, if this length is too long, and then if your number of visitors is limited, then maybe you should go back and then make some changes on alpha, beta, or D values, and then select an appropriate N value. But if you don't have any problem with number of visitors, right? So in other words, daily basis, let's say N is 10,000. So we ran experiments with 30,000 people. Let's say 30,000 people, all right? And then I don't have any problem with collecting 30,000 people on day one. I'm receiving thousands of people coming to my site every day, right? So in that case, what I'm going to do is I'm going to decide on a duration. Okay, in general, the duration is 1 week. Okay, I'm going to run this test for 1 week. There is a reason for that. I don't want to have my experiment finish on 1 day or 2 days or 3 days, because there is always this effect of novelty. Effect of novelty means when people see something new, they try it, right? So when you see a button red, oh, you wonder what is this red button, right? But we want to give enough time to our subjects that they are going to evaluate and then click on it, right? So we want to see that novelty effect lose its effect in the first 1 or 2 days, so that we can see the real impact of the change. But then if it is too long, then people are going to be familiar with that red color. The impact of red color is going to lose its impact because there are going to be some other changes on the website. So then the effect of other things will mix up with this red color. I don't want that to. So not too long, not too short. In general, 1 week, more or less, is going to satisfy the duration requirement. Okay. So let me, after mentioning this, let us talk about how we can evaluate the test results. No. So if you have a really small number of people taking the test, they are going to have t-distribution, but I'm assuming that we always have enough number of people taking our A/B test, all right? So we have enough number, so I'm gonna use z-test to evaluate our, again, if you know what is z-test and how you evaluate with z-test, evaluating with t-test is almost the same. You're just going to switch from z-distribution to t-distribution. Those who wonder what z is here, it is referring to standard normal distribution, and normal distribution with 0 mean and 1 standard deviation. Let me check if we have, oh. Can you define sigma? Sigma is, Ibrahim, sigma is the, let me write it here. Sigma is the standard deviation of the 2 groups. Now, normally, let's say group 0, 0, let's say group blue, okay, and then group red, all right? So normally these 2 guys might have different sigmas, all right? But remember, most of the time our null hypothesis, which is H naught, will assume that blue and red groups are the same. So we are going to compare our results based on this assumption. So if our result is statistically significant than what this null hypothesis is saying, then we are going to make some conclusions that, oh, null hypothesis is, we have enough evidence to reject the null hypothesis, because they are making this assumption for the null hypothesis, and null hypothesis says blue and red groups are the same. Then I'm going to assume that group blue has sigma standard deviation, and group red also has sigma standard deviation. They both have the same standard deviation. So because I assume those 2 groups are the same as part of the null hypothesis. And again, I'm going to compare my result with null hypothesis, assuming that that is based on assumptions around the null hypothesis. I'm going to compare my results with respect to the null hypothesis, and then I will have all my assumptions around the null hypothesis. Okay. Of course, it depends on the industry, but how can we define the D? Maybe we need to know what is the business definition of P0 and PA. Could you give some insight about this? So again, yes, that is totally correct. That it totally depends on the industry, on how the industry. Again, we don't know if you have a really large number of users, right? Let's say you have daily number of visitors to your site is, let's say, 1 million. All right. So in that case, a small d value might be sufficient, right? A very small d value. That means a small change on your site is going to have an impact on thousands of people, right? And then that change might be profitable enough for you to make the change, right? But if you have a small number of people coming to your site, then maybe the change is going to affect a very small, a fraction of your users. Then making the change is not going to be too much of a deal for you. So you are not going to even bother making the change. So again, giving insights about this, we need to really sit down and look at the number of people coming to the site. What is the cost of making the change? You have to also consider the impact of that change on entire populations, not just. So let's say the difference when you make the change from P0 from blue to red, the difference is 0.05. PA minus P0 is 0.05. So what does that mean? yes, that means on average, because I'm making the experiment on a sample I got from the population. On average, when I change the color from blue to red, on average, I expect that an increase in the click on the button. I expect that 0.05% more of my visitors are going to click on this button. And then what happens when they click on that button? Okay, so is it leading them to some another site where you're going to get more information about your users, or is it going to lead to a sale? So you need to consider what will happen, right? So when they click on that button, so if they are going to give more information about themselves, if that data is going to be valuable for, so you need to consider so many things for the impact of that change. So that's why it's very difficult for actually assess define the D value. It totally depends on the business. So yeah, I'm sorry, we're very vague answers, but again, it's hard to answer this question. You are asking hard questions today. Can you please explain what Z-test is? So Z-test, for Z-test, again, it's a different session. For I think I need another session for Z-test, but let me just tell you this. For Z distribution is a standard normal distribution with 0 mean and standard deviation 1. All right. So what we do is, given any normal distribution, let's say any normal distribution with mean and sigma, what we do is we take, let's say x is a random variable distributed normally with some mean and sigma value. So what we do is we take x, subtract mean from x, and then when we divide this with sigma, this operation is going to give me a normally distributed variable with 0 mean and standard deviation 1. That means for any normal distribution, if I do this operation on any normal distribution, then I'm going to always receive a standard normal distribution. So then I can use Z-test on this. So for Z-test, after we turn everything into a standard normal distribution, this is what we're going to see, this curve. So this curve is going to be 0 mean and 1 standard deviation, so that I can easily calculate this area. That is the purpose. That's why we call this standard. No, we standardize the normal distribution first, so that we can make these calculations easily. Right? Okay, Aisha, so you're interested in learning t-test. Again, if we have time, I can talk about t-test, but as I said, it's not so different. You're just going to switch from Z-test to t-test. Let us start talking about Z-test, and then if we have time, I'm just going to switch from Z to T, which is not a very big deal, actually. All right. Yeah, okay. I think, yeah, can you recommend some books on A/B testing? There is one book on A/B testing. I purchased it by recommendation of someone else on A/B testing. I read the first couple of chapters. I found it good, but I don't think it's going to, I mean, I don't think when you read the whole thing, I don't think you're going to read the whole thing. That's what, so essay. So I don't know the name of the, let me see, it should be somewhere here. Where did I put it? Yeah, I don't remember the name of the book now, but there is a book on A/B testing, specifically about A/B testing. I don't remember the name of the book. Just probably I'm going to remember soon. Okay, essay. Yeah, I'm very bad at remembering book names. Okay. Yeah, I said I'm going to talk about Z-test. So yeah, let's start talking about it. Let's say I ran an A/B test. All right, I ran an A/B test. And in my A/B test, I'm just going to write the numbers here. I have a control group, okay? The control group is the group representing your null hypothesis, all right? The control group is the one, in this case, taking the blue button, okay? And then you have the experiment group. Some call this treatment group, okay? Or treatment group. So these guys are representing your alternative hypothesis. These guys are the ones who took the red button. Okay, red button versus blue button. So I'm going to use these words. So I'm going to say number of people, okay, who took the what is that? Who was in the control group is 9,000. I don't know, 890. Okay, some number. So let's say you decided to use 20,000 people. You divided your group into two. One group is 10,000, the other one is 10,000. But in reality, you may need to exclude some of the people from the experiment. So you end up with these numbers. Your experiment is again 9,945. All right. So they are not exactly 10,000 because you had to exclude some of the people after the test. Something happened and then you had to exclude them. And this always happens, by the way. But know that at the beginning you decided that total number of people who are supposed to take this test is 20,000. You divided this into two equal pieces, 10,000 control group, 10,000 experiment group. Let's assume that we are running this blue and red button, all right? And then you count how many people clicked on the blue button, how many people clicked on the red button. We can simulate this if you like. I did this for another study. We can simulate, but let's say we only have the results for now. Okay? So number of people who clicked on the, what is that? On the blue button is, let's say, 1,254 people. All right, so this is number of people who clicked, and then number of people who clicked on the red button is, I don't know, let's say let's make this a little bit bigger. All right, okay, 1,356. All right, so this is the result we get. Okay, this is the result. We ran the experiment, and then somebody shared with us the results. So the first look gives me the impression that, you know what, the experiment group, I have more number of people clicking on the button. It looks like red has an impact, okay? But then the difference is not too high. It's almost like 100, difference of 100. It's less than maybe 6%. To me, it's significant. But statistically, is it significant? I just want to know that. All right. So that is why I'm evaluating this this experiment. So I want to make a decision on whether this experiment is statistically significant. All right. So what was so somebody decided on alpha value before us, right? So what was the alpha value? So let's say people decided that alpha value would be 0.5. All right. So people decided alpha is 0.5. Let me also silence this and then run this so that I have the values entered. Okay. All right. So alpha is 0.05. Somebody decided that. Now I need to actually, given this significance level, let me write this significance level. I need to now find out if I actually have any statistically significant result. So before I start with anything, let me first calculate the ratios. For that, I'm going to use letter C for control group and letter E for, what is that, experiment group. So the ratio of people who took in the control group is actually those people, I use the same words. Let's make this N and N. So let's make this X. This one X. Sorry, I should use X. So N is the total number of people who took the test. X is the people who clicked. Okay, let me run this and then correct it. Okay, so for the control group, the ratio of people who clicked on the button is actually X control divided by N control. Similarly, ratio of people from the experiment group who clicked on the button is X experiments divided by N experiment. So I found these two ratios now. All right. Okay. Now, here is the part where we need to a little bit think why we are doing this. All right. Remember what was the null hypothesis? The null hypothesis is that both groups are the same in their behavior. That is null hypothesis, right? So we are going to assume that is the reality. And then we are going to test this assumption by checking our results from the experiment. Okay, that is what we are doing now, right? So that's why now I'm going to create this pooled p-value. So p pooled hat. So what p pooled hat is, if these two groups are the same, according to my null hypothesis, then what is the ratio of people who clicked on the button? Now, I'm saying that there is no distinction between red and blue. It doesn't matter. So that is my null hypothesis, right? So what is the p pooled hat in that case? So it is how many people clicked on the button, X control group plus X experimental group, divided by total number of people who take the test. What is that? N control group plus N experiment. So I am just looking at the whole group, which is combination of control and experiment, the whole group. And then my assumption in the null hypothesis that these two groups are behaving the same. Okay, so that's why now I'm finding the ratio of people who clicked on the button. All right. Now let me run this. Remember from our early discussions, let me go all the way up, just to remind you that we already looked at those things, and there is a reason that, remember I said there is a reason why we're looking. Okay, here. So we looked at the variance of ratio, right? So I think we looked at it somewhere here. Yeah, sigma squared is p times 1 minus p divided by n. So the ratio is normally distributed with mu equals p, and sigma squared is p times 1 minus p divided by n. So we discussed this in our very first session. So, and then remember I said we are discussing this because we're going to use these numbers later on when we evaluate our test results. So that's why I spent time back then, so that we have that good understanding of it. So now, given this p-value, can I find the variance for this pool? Okay, so this is the ratio for the pooled group, which is the combination of both groups. So I have two groups. Okay, I have two groups, and if I have two groups, let's say x1 and x2 are two groups, and then x1 and x2 are representing two random variables coming from the same distribution. Let's say I'm flipping a coin, holding it, and then flipping a coin again. So the first and second one are coming from the same distribution, and they are independent. So in that case, the variance of x1 plus x2 given x1 and x2 are coming from the same distribution. I mean, they are IID distributed. Okay, let's say are IID independent and identically distributed. They are independent and identically distributed. So I can find this variance is variance of x1 plus variance of x2. Okay, so let's just keep this in mind. It turned into markdown. I know that we are getting into math now, but we are going to get rid of this soon. So we understand clearly what p pooled hat is. Now for these two groups, I'm going to calculate the variance. Okay, variance is actually it's nothing but p pooled hat times 1 minus p pooled hat times 1 over n con plus n 1 over n experiment. All right. So now you may just wonder what this means. So again, what is the variance of the first group? The first group. Okay, and let me call them blue group blue. Or let me just group blue. Okay, so given that blue group and red group are both coming from the same pool, and the p of that pool is this p pooled hat, right? So going all the way back, and then if you remember this again, Sorry for going back and forth. This one, P times 1 minus P times N. So let me write this down so that you know why we are writing things. So that's what I'm trying to do now. So this is equal to P times 1 minus P divided by N. Okay, that is coming from what we discussed earlier. So what is P for the blue group and for the red group? It's the same because they are from the same group. So let me just take this, put it here, and then put this here. What is N for the blue group? It is N control group. So I'm going to do the same thing for the other group too. This is the red group. Again, they have the same P, but their number is experiment. Okay, these are their variances. So when I add these two, x1 plus x2, it's the variance of x1 plus variance of x2. So that's why I'm going to say pooled variance is P pooled hat times 1 minus P pooled hat. So normally we just memorize this. I'm just trying to give you some intuition about why that is so. Times 1 over N control. I just took this N control and put it here. Plus 1 over N experiment. Okay, so if we go step by step, what we did is we first calculate the ratios for the individual groups. 2, calculate the pooled ratio. 3, calculate the pooled variance. Okay, so that's what we did. We are right here. This is the third step. Okay, remove this. Now, please remember, our null hypothesis is that these two groups are the same. And given this assumption, we are making our calculations. Then we are going to compare our result with this assumption. Are you guys with me? I know I see that. Okay, t-test. So, okay. No questions. All right. Let me know, okay, if you have any questions about this point, because they are very close to getting the test statistics now. Once we get the pooled variance, we know that standard deviation, STD, sorry, we know that STD is square root of variance, right? We know that. So once we get the pooled variance, I'm going to get the standard deviation. Let me call this SE, capital S. That is the standard deviation of the pooled group, okay? Which is, for that, I'm going to use NumPy. Let me import NumPy here. Import NumPy as NP. And then it's going to be NumPy square root of pooled variance. Perfect. So I got the standard deviation for the pooled group, which is composed of both blue and red. Assumption is that they are both coming from the same distribution. Okay, I hope up to this point things are very clear. All right. Next. So pooled variance and standard error, okay, for the pooled variance. Okay, that's the third step. Now, remember our null hypothesis. P naught equals PA. That is our null hypothesis. Remember the alternative one. Okay, maybe we are going to say PA for this case, let's say is not equal to, okay, is not equal to PA. Oh, I'm sorry, P0. That is our alternative hypothesis. Now for the alternative hypothesis, so for compare alternative with the null, so we can write this way. P alternative, okay? P0, I'm going to write it in the same order, is 0, okay? That is what we are assuming. So we are interested in this value, whether this is being equal to 0 or not, okay? That is our interest. All right. Okay, very close to getting some results. Any questions up to this point? Okay, so the next step is I'm going to get my test statistics. Okay, test statistics means let me get into it in a moment. Let me find the critical value first, and then I'm going to get to test statistics. So remember, I made an assumption about alpha, and then I'm testing P alternative is not equal to P0. So alpha, which is 0.05, is the area under the curve. Did we create both? No. Area under the curve on the right and on the left-hand side. Okay, so if you are doing a two-tailed test, alpha is the area under the curve on the right and on the left tail. So if alpha is 0.05, then this area on the right is going to be 0.05 divided by 2. Okay, so if you are, again, doing a two-tailed test. So that's what we are doing here, because I assume P alternative is not equal to P naught. So given this alpha value, I'm going to divide it by 2 so that now I have equal tail areas. Okay. Now alpha over 2 is the area under the curve to the on the right hand side, under the curve at the tail of the curve. If I subtract this from 1, okay, then I'm referring to the entire area under the curve, to the left of this red line. Okay, 1 minus alpha 2. So I'm trying to determine this value here. Again, alpha is the value of the area. The red line is corresponding to some probability value. When I find that probability value, that is when I find this value on the x-axis, that is going to give me this probability, which is the area under the curve. So if I know the area under the curve, which is 1 minus alpha over 2, okay, cumulatively, if I come from left to right up to this point, that is going to be the area. Then what is this point? Question mark. That's what I'm looking for now. I'm going to call it Z critical value. Okay, so given this 1 minus alpha 2, remember, this is nothing but the area under the curve up to that critical point. I'm going to use distribution norm. But before doing that, let me import norm. I know that I didn't import it. And then I see a question. I'm going to check the question in a minute. So I'm going to use SciPy dot stats. I'm going to import norm, right? So norm dot. So I'm calculating cumulative distribution function of 1 minus. I'm sorry, not cumulative. I'm sorry. Cumulative distribution is going to give me the other way. I'm going to calculate PPF. So what is PPF? Let me just write it here very quickly. PPF will give me the value on the x-axis that would be the border line for the area under the curve. So this is my explanation to myself. Okay, what PPF gives me. So if I know the total area under the curve up to this red line, and I'm curious what is this red line is corresponding to, for that I'm going to use PPF. PPF is going to turn this cumulative area back into this little point here. So if I know this point, I know that the area under the curve up to this point is equal to, let's say, 0.975. Then what is that number here? Okay, that's what I'm looking for. And PPF is going to give me that value. Okay, now let me make this equal to the critical value, which is very critical. Okay, so let's keep this in mind. Okay, I got let me just, here, it's 1.96. Actually, it's 1.96. Remember, we used this number here, 1.96. 1.96. Z 1 minus alpha over 2. Alpha is 0.05. So you got where this 1.96 is coming from in this equation for n, I hope, right? Okay, so let me see if I have any question here. Would you please tell me if you will teach Python in parallel with statistics? Yeah, I also have, so I teach normally statistics with Python, but I haven't started. I don't have any plan, Ibrahim, right now to start another, because I need to finish time series first. There is another one we started and then we couldn't finish. Remember, I'm teaching, what is that? Deploying a model. So we couldn't finish that one. So I'm going to go back and finish that one. And maybe then if I have time, we can start talking about from the very beginning, statistics with Python. Okay. Could you please give us some advice on how to get industrial experience running? I think the best industrial experience is running the A/B test, because it requires cooperation between you as the statistician or data scientist, and a software engineer, somebody maybe in charge of what is that, the architecture, and then the marketing group. So there are so many people who are involved. So the product manager or product developer. So we are testing something, right? Some product, something. So it requires input from many parts of the organization. Like let's see, at least 3 parts of the organization. I would say it sounds simple, but it is not very simple. Coordinating between these different groups and then starting running an A/B test. So the best industrial experience is actually working in a group. Okay. You can run your own A/B tests to gain some experience. It's not that difficult. We are sometimes running experiments, very simple. Say you create some advertisements and then change the advertisement details from one to another, and then run a 1-day experiment or 7-day experiment, $5 a day budget at Google or Facebook, and see what is the impact of making that change on your advertisement. So that would be a very good A/B test experience for you. You can do it very quickly yourself, actually, and then evaluate your results just following these steps. Evaluation is not a big deal. What's my GitHub page? My GitHub page is not so full. I'm not using GitHub so much, but let me search and then. Yeah, this is my GitHub page, and let me share it too. No, share. Okay. Yeah, I couldn't get the. I couldn't get the link to my own page. Let me share this one with you. So maybe I'm going to put the material here in the future. Okay, I'm going to put a post on there. Again, there's not much because I'm not using that much that page. As an overview, there are good A/B test examples in Kaggle providing data. And yeah, there are really good A/B test examples in Kaggle. I think at some point I got some part of this. Maybe another A/B test that I was using in my class. Yeah, I got that from Kaggle. So there are a lot of good examples at Kaggle, actually. Yeah. All right. So Z critical value, we calculated the Z critical value. Remember, we calculated. So that's the next step. Calculate the pooled variance. Okay. Z value. Okay. So next, so we calculated the SE, we calculated the pooled ratio, and we calculate Z. Now let's calculate the test stat. Okay, test stat. So what is test stat? When you turn your distribution to a Z distribution, I think I wrote somewhere here when I was trying to explain what Z is, Z test is. Here, right? This one. This one. Let me copy this for you. All right. Let me copy this for you. I'm trying to explain why I'm using this and that. So if you already know, it's going to be boring for you, but I don't believe the value of just giving some formula. It's not going to be so beneficial for us. So we know what this is. So given a random variable with some mean and sigma, I can turn this normal distribution into a standard normal distribution. All right. So that's some information I shared with you. Now, our null hypothesis is saying that P0 minus PA is 0. All right. That is our null hypothesis. Now, our null hypothesis is a normal distribution, which is, say, represented by this blue line. And our assumption is that its mean is 0. What is our null hypothesis? The distribution we are looking at is P minus P0 minus PA. I'm looking at the distribution of this difference. Okay, P0 minus PA is, I'm looking at the distribution of P0 minus PA. This blue line, let's say, is representing P0 minus PA. And our assumption about this P0 minus PA is that it's a normal distribution centered at 0. Okay, because that is what we are saying. Its mean is 0. Its mean is 0. So I'm going to write another thing here. Instead of X, this time I'm going to write this P0 minus PA. Okay, instead of X, I'm writing P0 minus PA. Okay, now I'm going to standardize this distribution, turn it into a normal distribution with 0 and 1. Okay, so then what I need to do is take X, which is P0 minus PA, and subtract its mean. What is the mean? It's 0, right? It's 0 because that's my assumption. P0 minus PA is centered at 0. Okay, so I subtracted this minus 0, all right, divided by sigma. What is sigma? What is sigma? We found sigma here, right? Pooled variance. What is that? The sigma here is standard deviation. Pooled variance and SE. We found it already. Where is it? SE right here. Okay, I'm going to put SE here. So the moment I do this, what I find is I find the value corresponding to P0 minus PA on a standard normal distribution. Again, if I had repeated this experiment over and over again, 1 million times, I would get P0 minus PA values, 1 million of them. If I had created a histogram of these 1 million P0 minus PA values, my assumption is that I would get this blue line centered at 0. That is my assumption. Okay, that is my null hypothesis. If I had repeated this experiment 1 million times and then get the ratios P0 and PA, take the difference, okay, and then plotted a histogram for this 1 million PA minus P0, P0 minus PA, it would look like a normal distribution which is centered at 0. Now, I will take this normal distribution and standardize it. It's very simple, a simple transformation. And that's what I'm doing here. So for this specific P0 minus PA value, if I standardize it, if I take that P0 minus PA value from my regular normal distribution, what will be the corresponding value if I turn this into a standard normal distribution? That is what I call it test stat. All right. So let me stop here and then see if you have any questions. Yeah, thank you, Engin, for sharing the link to this practice, A/B testing practice. Thank you. Okay, so I already found test stat. So please, if you are going to see this value in most textbooks, okay, they're just going to put this. What is that? P. So this one. Okay. This one minus this one divided by SE. That is the test stat. But why? What is this test stat? Why am I subtracting this? What is happening here? Why am I dividing this standard? That the only reason why I'm doing this is 1 point from a distribution that is the distribution of the difference between ratio of control group and experiment group. Okay, again, I'm repeating 1 million times. Repeat this experiment, it's going to give that distribution. This is only 1 point from that distribution. I am trying to find, if I had changed that distribution into a standard normal distribution, what is the corresponding point for this one on that standard normal distribution? So that's what I did here. All right. Okay, very good. So let me run this. Okay, I got the test stat too. Next. What I'm going to do next is, now what I found here, test stat is, I'm gonna go back to this blue line, okay? Remember, Z critical value was the value for this red line point. To find the Z critical value, I gave the area under the curve and got the critical value. This T stat is giving me what I found here, this T stat, this test stat is giving me a value on this line. Okay, a value on this line. Let's say a value here or a here. Now what I want to do is, what is the area under the curve to the right? Okay, then I know this point, T stat. I know this point now. I just want to find the area under the curve for this, so that I'm wondering if my T stat is falling to the right or to the left of this red point. Because remember, this red point is alpha over 2. If the area under the curve corresponding to T stat is less than alpha over 2, that means I'm over here. That means the area is small. Okay, I'm over here. That means I am falling into this area, blue area. That means I'm going to reject my null hypothesis. Right? So let's go and find it. So what I'm going to do now is I'm going to find my p-value. Okay, p-value again is the area under the curve for my test stat value. All right. So the way I'm going to find the area under the curve up to a point is normal distribution CDF. Now look, let me write for here. Normal distribution, cumulative distribution function. The normal distributions, if I do this, test stat. Okay, if I do this, test stat. So what is this? If I run this, what is it going to give me? Any idea? Let me run this. First, let me run this and then print it on the screen. Okay, it's 1 minus 199. Let me run this. It's 0.023. So what does that mean? Any idea? That's the area. Very good. So this is the area. So if I go back here, actually, if I go back here, where do you think? So my T stat is right here. The area that I found is area under the curve up to that point. Okay. This T stat has the exact the symmetric one on the other side too. So when I find T stat here, it is on the left tail. The same T stat has exact symmetric one on the right hand side too. So that's why I'm going to multiply it by 2 as I did for alpha. Remember when I was calculating number n in here, I was dividing alpha by 2 because alpha is representing the total area at the tails on both tails. So this T stat is only giving me the area under the curve on the left. How do I know on the left? From this value, negative 1.99. So what I'm going to do is I'm going to multiply this by 2 times. All right. So when I do this 2 times, I found the area under the curve at the tails. If I subtract this from 1, it is going to give me the area. What is that? It's going to give me the area under the curve, excluding the tails, right? Is that correct? Are you guys with me up to this point, or should I? Okay. Yeah. Let's finish this. Okay. Thank you. Thank you. So let's see what this value is. So 0.953 is the area under the curve, excluding the what is that? The tails. Okay, excluding the tails. All right. So let's continue, and then we are going to wrap it up. So for p-value, what I'm going to do is I'm just going to use my I'm just going to use this. Okay, this will be my p-value. And this 0.95 is 1 minus the p-value. So p-value is the area under the curve at the tails when you go to the right and to the left of t-stat values. Okay. Now, what is this p-value? Is 0.046. What is your alpha value? Is 0.05. So given this, what would you do? What would you make a decision about H0 and HA? Remember, H0 says P0 equals PA, and this guy says P0 is not equal to, sorry, PA. Okay, given this comparison, so what you found is if, let me write this, if p-value is less than alpha, what you're going to say is print, let's print reject the null hypothesis. Okay, so if p-value is less than alpha, that means whatever has happened with this experiment, it's so rare to happen. If I take my null hypothesis as correct, it's so rare to happen that I need to reject the null hypothesis. So let's see. It says reject the null hypothesis. That means our result is statistically significant that we need to reject the null hypothesis. What is the alternative hypothesis? That changing the color of the button has an impact on people clicking on it. Okay, that is what we just found by just comparing null hypothesis, the p-value with the alpha value. Yes. SE is the standard deviation of the pooled group. When you put blue group and red group together, what is the standard deviation for this group? Okay. Standard deviation of that for that sample group. Okay. Last thing before we leave for today, last thing, I think I'm also getting tired. Last thing. Yeah, so on the distribution of the null hypothesis, so on this distribution here, P0 minus PA, okay, on this distribution, we marked our critical value. Oh, let me also write the steps, calculate the p-value. Right, so maybe before this, I calculate the z test stat. Okay, p-value from test stat. All right. So what we did is we calculated the z critical value, we marked it, we calculated the test stat, we marked it. Actually, without even finding p-value, I can also write the following. If the test that is less than alpha, rejected. So I can even write this, right? If my test that is less than not alpha. What is that? Z critical. I can also write this, reject null hypothesis. So you can either compare test stat with Z critical or you can compare the areas corresponding to these two values, p-value versus alpha. Both will be fine. Okay. Now what we are going to do next is we mark the critical value, we mark the test stat value. I just also want to say how confident I am in terms of when I repeat this experiment so many times. Let's say I want to see 95% of the time I'm going to get the result falling within this range. Okay, if I had repeated this experiment so many times, 95% of the time, my experiment result is going to fall in between these two numbers. What I'm trying to say is, can we find a confidence interval so that when I repeat this experiment a million times, my experiment result is 95% of the time will fall within that range. Okay, we're going to find that confidence intervals. For that, I mean, in general, in the literature, in the industry, what we do is we mark our confidence interval by going to, by going to the left and to the right of our test results. So we ran the test, we ran the experiment, we got P naught, we know that, we got PA. And then we took the difference between P, 0 and PA. We got this difference, right? P0 minus PA. So we have this difference. Now what I want to do is, this is just 1 point. This is just 1 point. This is just one experiment. What if I repeated this experiment, right? So I want to have some interval so that in addition to this 1 point, I might have 1 million points. I want to have some intervals, and then I'm going to say that, you know what, 95% or say 97.5% of the time, the experiment results will fall in between these two numbers. Right? So for that, I'm going to create a new variable. I'm going to call it margin of error. Okay. So margin of error means, remember this. Remember what SE was? STD of standard deviation pooled group, right? So remember, this was, we found it here. Let's remember it. This one, pooled variance, and pooled variance is here. So let me just copy this here so that you remember what we are talking about. Out of this group, okay? So this is SE, all right? So we know SE, and we know what Z critical is. What is Z critical? Z critical is the value on the x-axis corresponding to the area of alpha divided by 2, right? This is the Z critical value, okay? So I'm going to multiply SE by Z critical. I'm going to call this my margin of error. So in other words, what I'm going to do is, let's say this is the number line. Let's say this is the number line. And in the middle of this number line, I'm going to put my P0, P0 minus PA, okay? So in the middle, I have P0 minus PA. So this number line is some interval. So I'm going to go to the right and to the left of this value. I'm going to go to the right and to the left of this value. How much I'm going to go to the right and to the left? That distance to the right and to the left is actually SE times Z critical. Okay, I'm going to go this much to the right and this much to the left. So that way I'm going to obtain some interval in which, if I receive my, if I had repeated this experiment, I'm saying that with some confidence, the results are going to fall within this range, and then see what this confidence interval is going to turn out to be. So first of all, let's find our marginal error, which is M. Okay, let's see what M is. Some value, 0.009. Next, I'm going to calculate my confidence interval. Okay, so for that, I'm going to get my P0 minus PA, which is this one. Okay, let me take this. And by the way, there is a reason why I'm multiplying this SE. Remember this test that is this divided by SE, right? So there is a reason for why I am multiplying the Z critical by SE. Let me first write this, and then maybe we can talk about it. We are almost done. I know we are all tired. We are almost done. So I'm going to multiply this. I'm going to subtract from this SE times, sorry, SE times Z critical, okay? And then I'm also going to add to this value. Now, where this is coming from, and then this will be our confidence interval. And let's call this CI. And then let's find this CI value. So this will be the confidence interval. Okay, this will be the confidence interval. So where this is coming from? Any ideas? Oh, there are some questions here. Yeah, so what is SE? Okay, what about CDF distribution? What is it? Cumulative CDF distribution. So CDF is nothing but the area under the curve, okay? Area under the curve up to a point. Yeah, you got your answering. Okay. Thank you. So anybody who would like to give some explanation on what this means, CI, confidence interval, and let me take some short break for myself. Where do you think we got this number from? So this why suddenly SE times Z critical? Yeah, any ideas? So this has to do with this, right? So this has to do, let's go back here, how we normalize our data. Did I find it here, right? It has to do with this, I'm sorry, with this formula here, right? So I'm dividing my probability by the standard error or standard deviation here to find the Z test score, the test score itself, right? So it is related to this formula here. I really don't want to get into now. I don't feel like I'm going to get into it, but it is related to this formula here, how we get the confidence interval. All right. So once you find the confidence interval, let's wrap this up and then finish it, because I feel like I'm really tired. So we found the confidence interval. So I think we can if you like, let me write the code nicely so that you get everything together. So let me put everything together so that we are going to leave this class with some nice piece of code. So I'm going to put this here. So first we found the ratios, okay, and then I put the alpha value here, okay, and then I got the variance, pulled head and pulled variance of this one. So let's see everything together so that we're not going to miss anything. Okay, and then I got the P pull head. Okay. And pulled variance. And then I got the Z critical value for that squared standard deviation. Now we got the critical value. Okay, so things are coming together now. All right. And we got the test stat. And then we got the p-value. Okay, almost done. And then the confidence interval. Okay, perfect. So I'm going to close it soon. So let me just go over the code together one more time. So see if anything I made any mistake so that we can close the session without any errors. So let me see. Oh, I forgot to put the norms. I know I used the norm at somewhere, which I couldn't find it. Yeah, here. So let's get this one. Okay. All right. So here are the results. This is my alpha value. These are the ratios, pooled, hat, and variance. I got the SE. I got the critical, Z critical value. So Z critical value. And then anything else, ISE. And then I got the test stat, Z critical value, the M value. This is M. So this one for you too. This is the marginal error. Okay, and I got the confidence interval. I think we covered almost everything that I plan to cover. I hope I didn't forget anything. Print CI. P value. Print B critical. And print. I'm going to share this at GitHub. Print M. All right. Okay, guys. Let me stop here for today. I think that will conclude A/B test. Our discussions on A/B test. I hope we were able to understand how we can evaluate the A/B test. Again, we find the p-value. If p-value is less than alpha value or alpha over 2, depending on how you test, double-sided or one-sided. If it is double-sided, you are testing PA is not equal to P0. If it is single-sided, you are testing either PA is greater than P0 or PA is less than P0. Depending on single-sided versus double-sided, you're going to use alpha or alpha over 2. You compare your p-value with alpha. We know what p-value is now. You can reject or accept the null hypothesis. You know what type 1 and type 2 errors are. One thing maybe we couldn't cover so well was confidence interval. So for that, I tried to give the formula, the margin error, and then we are going to go one margin error to the left, one margin error to the right of our confidence interval. Normally, for us to accept the null hypothesis, or for us to actually reject the null hypothesis, this confidence interval should include what is that our t-test value, right? So let me and then t-test value, if it includes 0, we are not going to reject the null hypothesis actually. Let me stop here, and then hopefully we can continue next time with time series, right? So thank you for listening, and let me know if you have any questions. I won't be able to answer now. I feel very tired now. I'm sorry, but maybe I can answer in our next meeting. So thank you very much for listening. I'll see you guys next time.